Welcome back to ece442 542. Homework number 3 is due tonight. And if you haven't checked your email, there are hints, or there is one hint for problem number 4 on homework number 3 if you're still struggling with problem number 4. Homework number 4 is due a week from today, and that will also have some additional material that you might want to look at, and that I'm labeling lecture 4.3, which was pre-recorded, and it comes in 2 parts, basically 30-minute installments if you watch the video, but there's notes, and that's dealing with state space representation, doing the zero-order hold approximation, or zero-order hold equivalent with state space representations. We've been looking at G of S forms of that, and we'll see a picture of that when we get into the summary square of zero-order hold equivalents. But before we get that, exam number 2 review session will be a week from today, and it will be in this location, and it will start shortly after the lecture ends. So it'll be a late night. Make sure you sleep. Well, I guess you could sleep through the lecture and then you can wake up for the review session. How's that? All right, heads are down now. Bring your I'm just returning things that were left during office hours. So if you're wondering if I'm passing out information that you should be getting, no, it's not. It's just I want to return things to their rightful owner. But if you have questions about this material, you can submit those on a quiz that is now set up for exam number 2 on B2L. And exam number 2 is a week from Wednesday. And I have also posted a project description for those of you in 542 if you're wanting to get some insight into that and maybe get started over spring break. Hopefully you now have that available to you. The Wednesday of our exam, next Wednesday, is the last time we will meet until spring break is over, right? So that's our last time that we will meet until you return from spring break. We won't see each other quite a while after March 8th. There's a lot to cover between now and exam number 2, and there's only 3 lecture periods. But today what I want to do is present a table that contains our zero-order hold equivalents that we've already derived, just so that it's there in a form that you can sort of compare the different systems with. Then we will look at a summary square of zero-order hold equivalents, which we can work our way around, and it's a state space representation leading into the time, or leading from the time domain to the frequency domain, etc. That will make more sense when I get to the picture. I'm not sure when I will do the derivation of the zero-order hold equivalents by hand, but I will try to derive some of those expressions that we've used to fill in our table, today's table, based on the table of z-transforms. Last time in our lecture we were just saying, oh, from table line number such and such, here's the transform pair. But it might be nice to know or have a better understanding of where those transform pairs are coming from. And that's what I'm meaning by maybe doing a zero-order hold equivalent of some of these transform pairs by hand. As I said earlier, you can look at lecture 4.3 for the zero-order hold equivalent of the state space representation. And if you are following along and memorizing everything that I've been saying, there's many different ways of performing a discrete equivalent. So far, we've looked at the zero-order hold equivalent, which is where the system is preceded by a zero-order hold. Today, what I want to cover are these discrete equivalents that are not preceded by a hold. And we'll look at 2 different varieties of those. We may not get to the pole zero mapping. That may have to happen on Wednesday. But today, hopefully, we will talk about numerical integration techniques for performing discrete equivalents, and those will come in 3 different flavors: a forward, a backward, and a trapezoidal flavor for the discrete equivalents. That's where I want to go today. As a reminder, I'm going to scroll through some material that hopefully is just to get us back on the same page. We had two different scenarios for discrete equivalence. Scenario number 2 is the one that we covered first, which was dealing with the case where we were trying to go from g of s to a g of z, but we had the scenario where a zero-order hold was actually preceding our analog plant, and we wanted to incorporate that dynamic behavior of the zero-order hold in the total discrete time representation, which we've now labeled capital G of Z. That was our zero-order hold equivalent using, that was a discrete equivalent using a zero-order hold equivalent approach. And that involved, if you remember, that ended up saying, oh, you want the zero-order hold equivalent? You could just use this definition. That's 1 minus z to the minus 1 times the z transform of the plant, g of s, whatever that plant is, whether it's an integrator, a double integrator, a first order, a second order. You now simply introduce one more pole at the origin and z transform that new expression, multiply it by 1 minus z to the minus 1, and that is now your zero-order hold equivalent of that g of s. That was actually scenario number 2. And that gave rise to the following different pairs of, or ways of connecting different kinds of systems. Here I have the description on the left. In the center is what that g of s looks like in the s domain. And then in the right-hand column is the result of performing the zero-order hold equivalent for that particular system. We had a pure gain. We had a gain in the analog setting that translated into a pure gain in the zero-order hold equivalent. Yes? So this is the zero-order hold equivalent, which will behave, you might have heard this referred to as a step response equivalent, but that's what this can be called also. But I'm trying to be consistent and call this our zero-order hold equivalent so that you're clear that this now incorporates the dynamics of the zero-order hold. No, we're not really trying to find, this question was, are we trying to find the step response of a system? No, we're not. But we are trying to find a discrete time transform that we can now use either for design or analysis purposes. And it now incorporates the influence or the dynamics of that zero-order hold. And we have it for a pure gain, an integrator. Now we have a pole at z equal 1 in the g of z, and that's consistent with a pole at the origin in the s domain. If we had a pure mass or a double integrator, now we have two poles at z equal 1, and we also now have a 0 at z equal minus 1, which is a very fast 0 in our zero-order hold equivalent. And if we simply had something as straightforward as a first-order system with a gain k over s plus a, now we end up with a g of z that maybe looks messy, but it's really very similar to this first-order system. If you look at where the pole is sitting in the z domain, that's at z equal to e to the minus at, which is consistent with a pole at minus a in the s plane. And you could compare the DC gains of these two. What's the DC gain in the middle column of a first-order system? How do you find the DC gain? What's the frequency of a DC signal? 0, right? So now if we wanted the DC gain of a first-order system in this expression, we have k over 0 plus a, or k over a is our DC gain. That's what the gain is. If we injected a DC waveform, it would then get scaled by this amount, k over a, in an analog setting. What's the DC gain here? Well, now we need to look at what happens when z goes to 1. There's only one z in this lower right-hand column of that table, or element in that table. We have 1 minus e to the minus at, but that's exactly what you have as one of the factors in the numerator, and what happens? Those cancel, and what's our DC gain for that zero-order hold equivalent? K over A. It's exactly the same as what our DC gain was for our first-order system. There is some consistency between the zero-order hold equivalent in the discrete time setting and the system that we're now trying to go from continuous time to discrete. Right on cue. Ben? Yeah, now we know who's knocking, right? Here's our playing surface for our summary square of zero-order hold equivalents. I know it's busy, but it's available to you. You don't have to copy all of this down. What I want you to do is try to absorb this. The left-hand blocks are the continuous time case. The right-hand blocks are discrete time case. Meaning, if we had a state space in the time domain, that's this x dot equal ax plus bu, then if we sample that with a zero-order hold on the input, we're going to end up with the state vector x at time step n plus 1 is equal to some capital phi matrix. That's a Greek symbol. That's just a matrix. X at time n plus gamma u of n. And below I will show you what phi is. Phi is just this matrix exponential. If you can find this matrix exponential and substitute capital T, your sample period, into that, you will now have your system matrix for the discrete time system in a state space form, and it's a zero-order hold equivalent. This is lecture 4.3. I'm summarizing. This is 30 minutes of explanation, which I'm not going to do today, I hope. I want to just go through, or just tell you that this is what we have. And hopefully the bottom row, which is the frequency domain version, is familiar. If we simply had a G of S, which from our cheers in earlier classes, we know how to get G of S from a state space representation, right? We know the cheer. C times Si minus A inverse B plus D. It's not that important if you don't remember it, but if you had a state space representation, you could obtain a transfer function, capital G of S. But if we have a G of S, we know how to find the zero-order hold equivalent. That's just 1 minus c to the minus 1 times the z transform of G of S over S. If you now had your system in the time domain state space representation with phi, gamma, c, and d, then we would have a transfer function, G of z, in terms of those state space matrices as c times zi minus phi inverse gamma plus d. Exactly the same structure that you've seen before for the continuous time. It's just now that you're having this operator z, which corresponds to a unit advance, or z to the minus 1, which corresponds to a unit delay. That's our summary square. If you know how to chase your tail around this square, you'll be okay for maybe this part of exam number 2. This part. That's the key. This is just a part of exam number 2. It's not the whole thing, but it's a part. Let's look at where we are again. Here's discrete equivalence with respect to block diagrams, and these are closed loop block diagrams. And we've already covered scenario number 2. We were now trying to find a way to describe the zero-order hold, the analog system, and the A to D converter, put all of that into a transfer function in the Z domain, and that was now our G of Z. What we want to cover today is what I've now dashed in red and described in red, and that is to find this discrete equivalent, capital C of Z, starting with a capital C of S. And do you see a zero order hold or any kind of hold before that? No. All we're trying to do is go directly from a C of S, which could be a filter, it could be a controller, to obtain a C of Z. That's scenario number one, and we're trying to now determine how can we go from C of S to C of Z. That's what we want to work through today. Or another way of saying that, here's another block diagram. We're going from an input U to an output Y through some filter or through some controller in both scenarios, except one's for the continuous time case, one's for the discrete time case. We want to know how do we obtain the capital C of Z given a C of S. And what we're going to do today is we're going to start with a C of S that's maybe a first order filter. That should make you feel warm and fuzzy. If we now have a first order filter, you know what C of S should look like as a first order, let's say, low pass filter. What does that result in for capital C of Z? And we'll see various ways of finding different C of Z's based on how we make this discrete equivalent. Or for today, we'll probably be focusing on numerical integration techniques. Let's get started. Now that all the commercials are out of the way, I'll view those as commercials that we just had. Now let's have the movie, the main feature, start. Okay? So now we need to pay attention. Hopefully you've ingested your popcorn, you're really up with your caffeine, and now you're ready to watch. I don't know if there'll be any awards at the end of the season for this movie, but maybe. What? Graduation. That will be your award ceremony at the end of this. So make sure you're getting this so that you can graduate, right? You want to successfully complete this course so that you can go to the award ceremony, which is graduation. Let's look now at these three different ways of performing numerical integration, which is just one way of finding a discrete equivalent. But now we're doing it so that we don't have to worry about this preceding zero order hold. What's the idea? Let's look at now a picture of what we mean if we're now performing numerical integration. Suppose that I now have a waveform, let's call it x of t, and I want to know what's the area underneath that curve. That's integration. Yes? We went back to calculus and they said, oh, let's do an integral. Then what are we doing? We're finding the area underneath the curve. Now we have the curve, x of t. We want to know how do we find the area underneath that curve, and we'll call that area y of t. And the way that we'll do this is we're going to do this in steps. Meaning we're going to identify, let's say, a point on the x of t curve. Let's call this x at time step n minus 1 capital T. And let's call this point, I'm exaggerating the spacing so that you can see what's going on. Let's call this x of t, but now t is getting sampled, so this is now little n capital T. Meaning, if we now look at the area under that curve up until this point, which is now, let me call this t minus t, but we are going to replace t with nt, so this is nt minus t, or this is n minus 1 capital T. That's this point in time. We want to know what's the area underneath this curve up until that time. And that's what we will call y of t minus capital T. But we will also want to know what's happening as we evolve in time, so that when we get to this point, which is now time t, or when we sample it, it's now time little n t. Now we want to add in this additional piece, but the total is all of that, including that little sliver that we've now just introduced. And the numerical integration, the different approaches are how do we approximate this red piece. We could approximate it with rectangles. We could approximate it with trapezoids. That's going to give us our forward, our backward, and our trapezoid rule. And you can anticipate where those are coming from. The forward technique for numerical integration is if we're standing at x of n minus 1t and we look forward, then you can see that our triangle, our rectangle in this case would be formed that way. If we did the backward, then we look at x at time step n, little n capital T, and we look back to where we came from. Now our rectangle would be that. And you can see there's an approximation involved. The trapezoid is to connect those two, so that we're taking the average of what the height was of x at time little nt and time little n minus 1 times cap t. Those are our three different approaches, numerical integration approaches. Let me write down some of the equations. Let's say then that y of t in general is this integral from 0 to t. Now we're just back in our calculus class of x of tau d tau. But we want to break this up so that we can iterate towards that y of t. Meaning, we want to now look at y of t. Let's say that's the area under the curve x of tau, or let me just call it x of t now because tau was just a dummy variable of integration. The area under x of t up to time t. Contrast that with y of little t minus capital T, and that's now the area under the x of t curve, except now it's only up to time little t minus capital T. And what we are going to do now is rewrite or express y of t in terms of what y, the area was one time step before, plus an additional piece, which is the area from t minus cap t to t of x of tau d tau. And the difference in all of these approaches is how we approximate that red integral, which is just that little piece that we might be approximating with rectangles or a trapezoid. And that's just going to allow us to add on or to numerically integrate this expression. We're numerically integrating a waveform x of t to generate y of t, which is just the area under the curve. In all of these blues and blacks and reds, let's now replace t with the sampled version. Let's replace little t with little n capital T, and then we'll be ready to go. And if we do that, now we have y of t, which is y of nt, is now equal to y of n minus 1 cap t plus this integral from nt minus t to nt of x of tau d tau. And this is the piece that makes the difference between all of these different techniques. The different numerical integration techniques are based on how this integral from nt minus t up to nt of x of tau d tau is approximated. And I tried to hint at what that looks like from just this picture that I talked about before. Let's now describe that in words. Here is our forward rule for doing a discrete equivalent using a numerical integration approach. We want to now approximate the integral, which is just trying to find that little sliver of area, approximate the integral with the rectangular area looking forward from x at time n minus 1 capital T. Or if we do that, now we have this integral that's not changed, but what is going to change is how we approximate it. If we're now approximating it with this rectangle, how do we find the area of that rectangle? How wide is that rectangle? Let's go back to our picture. How wide is this rectangle here? What's the width of that rectangle? It's from nt minus the quantity nt minus t. How wide is that? The nt's cancel, do they not? And we're left now with this particular width just being the sample period. And how high is it? Or what's the height of that rectangle? Well, now we're looking forward from x of n minus 1t. That's the forward height. I'm sorry, that's the height of that rectangle. It's x at time n minus 1 cap t times the width, capital T. That's all we're doing to make this approximation of that integral. Or down here, we can now say, oh, we're approximating that with t times x at time n minus 1 cap t. That's all we're doing. But now that allows us to simplify this difference equation. We know now that y, the area under the curve at time t, which we're now sampling, so it's little n cap t, we're doing an approximation, so it's approximately the area under that x of t curve at time nt minus t, that's just n minus 1 times t, plus that integral approximated. And in the forward case, we're approximating it with that t times x at time n minus 1t. So this is t times x of nt minus t, where this is now n minus 1t. What are we doing? If somebody gives you a waveform, x of t, and you sample it at capital T instances of time, now you could find the area underneath that by using this difference equation. If you said, oh, let's start at time 0 and say that we don't have any area up at 0, then you know how to initialize this difference equation. But do you see that there's memory built in? Once you start getting some area under the curve, that gets remembered, and then you add on a little bit more. It's just t times x at time n minus 1t. And now you know how to perform numeric or find the area under any curve x of t that somebody might hand you. You just need to sample that x of t and put it into this approach. It would now be the forward rule that you would be using. This is a time domain version. We like to think in both domains. Let's go into the frequency domain and see if that gives us any additional information. Let's go into the transform domain. And one thing, it's sort of nice to know that you have the ability to move back and forth. What happens now if I take this into the frequency domain? What happens to y of nt if I z transform that? This one's so easy, it's hard. If I gave you y, W-Y-E, if I handed that to you and said, give me the z transform, what would you have to do? You just have to pull out your typewriter, hit the shift key, and say capital Y, right? So, if I give you y at time nt, to z transform it, the left-hand side now is capital Y of z. And now I'm going to forget the approximation. I'm just going to go with an equality. If y of nt gives me capital Y of z, what's little y of n minus 1t produce in the transform domain? That's just a 1-unit delay of y of z. Is everybody comfortable with that? And now, using the same connection with our typewriter and the shift key, how do I now find the transform of the approximation of the integral? What's capital T? That's just a number. That's a constant. So that just comes right out of the z transform. What happens when we z transform x at time n minus 1 cap t? Time shift in the time domain translates into a multiplication by z to the minus 1 in the frequency domain. We now have z to the minus 1 capital x of z. I hope you're getting as excited as I am with this. What are we going to get? Yes, you should be raising your pom-poms if you're cheering. I saw it in the back. I did, really. Oh, some of you don't like it. Well, bear with me. What are we going to get? We want to now have an input, x, and produce an output, y. What's that begging for? Give me a t, give me an f, give me a transfer function, right? Oh. Let's find the transfer function between the input x and the output y. The input x is a waveform. The output is the area of the curve, and this is in the frequency domain. Let's combine the y's. 1 minus z to the minus 1. You've probably seen that before. That's just 1 minus a delayed unit step in the frequency domain, equaling t z to the minus 1 x of z. To obtain the transfer function, we're just looking at y of z over x of z. And that just involves algebra. Now we have t z to the minus 1 over 1 minus z to the minus 1. And that might be all you do in 429, is leave it in terms of z to the minus 1s. But here, what do we want? We want it in terms of z's. How do we do that? Well, we can factor out a z to the minus 1 from the numerator and the denominator, or we can multiply by 1, which is z over z, and we end up with t over z minus 1. And that is now what? This is the frequency domain version of numerical integration. What? So let's connect this with what we're comfortable with. Let's go back into the continuous time case and then make the connection. Recall. What does integration look like in continuous time? And that one you should be able to just write down to please your calculus instructor. This is just y of t is equal to the integral from 0 to t x of tau d tau. That's the continuous time expression. But what if somebody says, take this into the frequency domain? Then what happens? What does little y of t become? Shift y, capital Y of s, right? That's the hard part because it's so easy. But what happens when we Laplace transform the right-hand side? What's an integral operation do in the frequency domain? What does that become? You know what a derivative does in the frequency domain, right? In the time domain, a derivative translates into a what in the frequency domain? Multiplication by s. So integration is 1 over s. We now have 1 over s, x, capital X of s. What's our transfer function? Our transfer function of an integrator for the continuous time waveform is 1 over s. What? Well, now we're there. What we want to do is compare these expressions. What we want to do is go from c of s to c of z, and if we have a way to map s into z, we'll be there. But we have two expressions, one for the analog, the s domain, and one for the z domain. Let's just compare those. If we compare the two transfer functions, now we see that 1 over s can be compared to capital T over z minus 1. And maybe we don't want to be standing on our head. I'm tempted, but I'm not going to. Do it. Yeah, I might pass out. Maybe after class. But what's this telling us? Well, let's just flip this. And I'm not going to do a flip either. But if we flip this, we could say, oh, now we have a more direct way of relating s with z. S is now z minus 1 over t. What does that tell us? Well, if we have a transfer function that has these s's around, that's our s domain filter, controller. Now we would just replace everywhere we see an s with this expression, z minus 1 over t, and we have our discrete equivalent. How easy can that be? And that's what? That's a numerical integration discrete equivalent using the forward approximation. Meaning, now we just, to make this happen, we replace everywhere we see an s. So if we see an s squared, we replace it with the quantity z minus 1 over t squared. We replace s with z minus 1 over capital T in h of s to obtain h of z. Now do you see where we're going? Now it's time to pull out our best friend, which is our low-pass filter, right? Let's look at a low-pass filter and take that from h of s to h of z. Here's our example. Suppose h of s is now a low-pass filter and if you were in an interview in Dallas or wherever, let's say now you have this interview and somebody says, can you give me a low-pass filter? And you go, of course I can give you a low-pass filter. First order, will that be sufficient? And they'll go, wow. They even know something about what I'm asking. They're asking about the order of this filter. What would you tell them? What would be a low-pass filter? H of s equals, and now you fill in the equal sign, or you put in the right-hand side. Yeah, you just put down the equals. Really, Thart just said I just had to do an equal sign, and that gives me a low-pass filter. Not quite. What's the right-hand side for this low-pass filter? I think it has a horizontal line. You could sketch a Bode plot. Yes, that would show some understanding of a low-pass filter, and it's going to be flat, and then it's going to go down. That's a low-pass filter, and I guess it depends on how you're looking. But in terms of a transfer function, what's a low-pass filter? And let's say it's first order. Where's that pole if I said s minus a? If a is positive. If a is a positive number, where's the pole of this filter? Right-hand side or left-hand side of the S-plane? This one is S equal A, and if A is positive, that gives me a pole in the right-hand side. Ooh, I don't want to hit my system that has, that would be an unstable. So let's do this. Let's do an S plus A. Now our pole is at S equal minus A. That's a stable location. That's a pole in the left half plane. And maybe I want a DC gain of 1. What do I put upstairs? A DC gain of 1 for this low-pass filter. A. And you'll get an A on your interview exam, right? With these little A's. I don't like that plus sign. It got a little aggressive. How's that? Now, what do we have? We have an analog transfer function with a pole at S equal minus A. Do we have a 0? Do we have a finite 0? Do we have a finite value of S that causes capital H of S to vanish, to become 0? Do we have a finite value of S that causes H of S to vanish? Is there any S in my numerator? No. We have no finite 0. The reason I'm saying finite is because we do have an infinite 0. If you let S go to infinity, H of S would vanish. Yes? So we have a 0 at infinity, but typically we just keep track of finite poles and zeros. The DC gain, by design, H of S, when S is equal to 0, was A over 0 plus A, which is A over A, which is 1. Now, what we want to do is design a difference equation that will implement a low-pass filter. And to find a difference equation, if somebody gives you a h of z, you can now take that back into the time domain to find a difference equation. And then you can put this into a computer and perform a low-pass filter with a difference equation. So before we do that, we need to find capital H of z using this capital H of s. Let's now find use the forward rule to find h of z. And to make this distinction, let me label this as h sub f for forward. That's not the grade that this poor transfer function is receiving. This is just labeling it as a forward numerical integration approach. This is now found from h of s in what way? Well, we just derived this relationship between s and z, and we said if we replace s everywhere with z minus 1 over cap t, we will have an expression for our low-pass filter in the frequency domain. This now, let me be as explicit as I can. Now s was the next thing in the denominator. I'm replacing that with z minus 1 over t plus a. And I'm done. If I didn't simplify, this is fine. But typically we want to clean it up a little bit. And that t in the denominator of a denominator term, that's kind of messy. Let's get rid of it. We can get rid of it by multiplying by 1, where our 1 is capital T over T. Or capital H sub f of z now becomes little a capital T. The z minus 1 falls out because I've now multiplied everything in the denominator by capital T. And I have an AT downstairs. Or I now have a transfer function in the discrete time case of AT z minus 1 plus AT. Let's now see what this has in terms of properties or characteristics. For this discrete time transfer function, where's the pole? And now when I say poles, you start looking where? Around the room? There's a pole on this music stand. I apologize for those of you. No, the poles are where in this transfer function? I'm blind, I can't see, but that looked like a pole to me. So where's the pole here? We set the denominator, we're looking at the denominator, and we find all the values of z where that equals 0. So now we set the denominator equal to 0, and we now have a pole at 1 minus AT. Does that seem okay? Where is that pole located relative to the unit circle? The boundary of the unit circle would be right at 1. Now we're just moving a little bit closer to 0, the origin, so we're inside the unit circle, and it depends on the sampling period, capital T, and the original pole location of our low-pass filter, which was determined by A. So if we had a low-pass filter with a bandwidth of 10 radians per second, little a would be 10. And capital T would be something to give us a reasonable value. It might be, what, 30 times that bandwidth. The T would be based on that. Do we have any finite zeros in this H of F sub Z, of Z? No, no finite zeros. And what about the DC gain? What do we what value of little z corresponds to dc in our discrete time setting? One, right? If you're thinking long at home, you're holding up that one finger. I appreciate that. Right? Everybody in class was just giving me the one finger, the index finger. Right? All right, so now we have h of z, z equal to 1. Let's evaluate that. We now have at over 1 minus at. Again, I had to make a plus sign in there. I made a mistake, didn't I? You didn't see it if you weren't listening. But it's now at over 1 minus 1 plus at. The ones cancel, and what's our DC gain? And that's consistent with what we started with. Is everybody comfortable? Now we've done a numerical integration-based discrete equivalent where we don't have to worry about a preceding zero-order hold. We just want to get or obtain a transfer function from an analog transfer function. And you could now put this into a difference equation by taking this, multiplying it through, and taking it into the time domain. All right, let's do another numerical integration. This is getting fun, right? Let's do the backward rule. Here we approximate the integral. Again with a rectangular area. But now we're actually looking backward from x at time little n capital T. Or now we have this nt minus t up to nt of x of tau d tau. Now we approximate it with its width hasn't changed. It's still the sampling period, but now the height is what the height is of x of t at time t, which is x at time nt, and we're looking backward from that point to get that little sliver's approximation of its area. And now you know the drill. What do we do now? Now we can find another difference equation that approximates this area under the curve. It's now y of nt is approximately y of nt minus t plus tx of nt. That's the time domain. That's begging us to now go into the frequency domain. Doing that, we have capital Y of z is equal to z to the minus 1 capital Y of z plus t capital X of z. And it's a little different than what we had before. So that now we have, can I just go ahead and find the transfer function? Y of z over x of z is now t over 1 minus z to the minus 1. I just pull the y over and divide by that factor that comes out, which is 1 minus z to the minus 1. Or if I clean this up and write it in terms of z's, I now have tz over z minus 1. Now I'm ready to compare the transforms. And if I compare the transforms, the integral in the analog case is just 1 over s, and that now is compared to tz over z minus 1. Or, if I flip both of those, I now have s being compared with z minus 1 over tz. And to get the discrete equivalent, I simply replace everywhere in my transfer function capital H of s, I have an s. I replace it with this expression, which is now z minus 1 over tz. And that looks similar, except now it has a z downstairs that didn't exist before. But that's what we put into capital H of s to obtain capital H of z. And now we go back to warm and fuzzy. I'm sorry, the low-pass filter. So now we have H of s. Let's not change that. It's a over s plus a using the backward rule. So that h sub b of z is going to be h of s with s replaced with z minus 1 over tz. Or this is now a over z minus 1 over tz plus a. And again, maybe that looks a little messy. But how do we know how to clean that up? Get rid of that denominator in the denominator, and we can do that by multiplying the denominator by capital TZ. And we can't just multiply a denominator by an arbitrary number. We can multiply by 1, which says now let's multiply that by TZ over TZ to yield the following. Now our transform in the discrete time setting using the backward rule of numerical integration is now a tz over z minus 1 plus a tz, or a tz over 1 plus at times z plus, minus 1. This is a little bit more colorful. Where's the pole? What value of z causes the denominator to vanish? One over 1 plus at. Where is that relative to the unit circle? What's at? A positive number, which we're adding to 1, and we're dividing 1 by something a little bigger than 1, so we're, again, inside the unit circle. This is seeming okay. Where's our finite? Now we do have a finite 0. Where is it? Right at the origin. That's pretty fast, isn't it? That's a fast 0. How many times does it take you to get from something to nothing if you had something at 0? 1 multiplication, right? That 0 is quick. Yes? All right, let's move on. What about the DC gain? h sub b of z with z equal to 1, what's that end up being? Still 1. Looking good, huh? So we have a pole inside the unit circle. We now have a finite 0. That's okay. It's fast. And we have a DC gain of 1. Let's do this another time. C. Now let's make that sliver approximation a little bit maybe more accurate. Let's approximate by averaging the left endpoint and the right endpoint to form a trapezoid. That's where this name comes. Or you might hear it referred to as a tungsten approximation. But we're going to go with trapezoid. Here's our trapezoid rule. Here, what are we doing? Again, all we are doing is approximating that little tail part of the area under the curve. Approximate the integral. By a trapezoid. Or we now have this integral from nt minus t to nt of x of tau d tau. The width of that integral hasn't changed. And what are we doing? We're now basically just taking the average of those two endpoints, the left endpoint and the right endpoint. This is now x at nt plus x of nt minus t all over 2. And really, this is like we are averaging the forward and the backward. It's one way to think of it. This now gives rise to our difference equation. Little y of nt is now approximately little y of nt minus t plus t over 2 times the sum of x of nt plus x of nt minus t. And you know where we're going. Let's now take the transform of this. The first two terms are exactly the same as they were before. We now have capital Y of z is equal to z to the minus 1 capital Y of z. Capital T over 2 is just a number. And eventually we will have capital X of z scaled by what? What's the first piece give us? Just capital X of z. That's now 1. What's the other piece in that combination of little x's produce? That's just a one sample delay of little x of n in the frequency domain. Now we get a little bit more color than we've had before, or y of z, capital Y of z over capital X of z is now, the denominator is what we've been seeing all along. That's just 1 minus z to the minus 1. In the numerator, we have the constant, capital T over 2, times 1 plus z to the minus 1. Or, we clean this up and write it in terms of z's. We have capital T over 2 times z plus 1 over z minus 1. if we compare the transforms, the integral 1 over s is going to be equivalent to t over 2 z plus 1 over z minus 1. Or, if we flip this on its head, we now have s giving rise to 2 over t times z minus 1 over z plus 1. Or maybe to make it look even more like what we've seen before, we could put this 2 in the denominator of the denominator, and then we have the z minus 1 in the numerator like we've had before, and then we had a z and a 1 before, and that's now coming in as z plus 1. If we're now wanting to go from h of s to h of z, we now know how to replace s. We replace s with 2 over cap t z minus 1 over z plus 1. Everywhere we see an s in h of s, that gets substituted to obtain our h of z. And now we're ready to go back to our low-pass filter using the trapezoid rule, or maybe somebody might even say the bilinear transformation. Bilinear, why does it say bilinear? Well, you have linear, and then you have bi, and you put those two together. Bi means what? 2. So you sort of have 2 pieces that are linear in a sense. So you kind of combine 2 linear pieces, and now you have this bilinear transformation. All right, let's find now, and now I don't know where to, I can't call it b, can I? H sub b, that would be confusing with the backwards, so let me call it h sub t for trapezoid. I now have h sub t of z is now h of s, where s I'm replacing with capital 2 over t times z minus 1 over z plus 1. Or, this is now a over 2 over t, z minus 1, z plus 1, plus a. And we can clean this up again like we've done before. We can multiply by t times z plus 1. Or we now have a t z plus 1 over 2 z minus 1 plus a t z plus 1. Combining our terms that are weighting the z, we have 2 plus at z plus at minus 2. And that's now our h of the trapezoid rule of z. Where's our pole? Is that where it is? So now we're just we're just solving for the denominator equal to 0 and solving for z. That will give us our pole. And where does that look like in terms of relative to 1? Sort of sneaking, so 2 minus AT, that's a little less than 2, and 2 plus AT is a little bit bigger than 2, so again we're less than 1, so that's good. Where's our 0? Z is at minus 1. Again, that's a fast pole. That's if we went around on the on the unit circle to go to sort of our final destination, which is Z is equal to minus 1. And what's our DC gain? So now we have 2's are wild in this case, aren't they? In the denominator, if I put in 1, I have 2 plus AT minus 2. I have 2 ATs. And what do I have upstairs when I replace Z with 1? A 2 times AT. Looking pretty good, I hope. Is that correct? So we have a DC gain of 1 in all of these approximations. We have poles inside the unit circle, and they differ by where they may or may not have a finite 0. If we're using these discrete equivalents using numerical integration, is it preserving stability? Meaning, if I had a stable transfer function, capital H of S, am I guaranteed that my H of Z will remain stable? Here I'm not worrying so much about causality or anti-causal. I'm assuming we're now working within non-negatives. This is a causal system. We want to know, do we have our poles inside the unit circle if we start with our poles in the left half plane for H of S? Is stability always preserved with numerical integration? And the way that we can investigate that is we can check the mapping. And this is actually getting us ready to jump into the pole zero mapping technique of discrete equivalence on Wednesday. But let's now check the mapping for stability purposes from the S plane to the Z plane. First, let's look at the forward rule. Which said that we replaced S everywhere with Z minus 1 over T. But now we want to go from S to Z. So let's just solve this equality for Z in terms of S. Or if we multiply both sides by capital T and add 1, we end up with Z being equal to ST plus 1, or 1 plus ST. Here's my S plane. Here's my Z plane. I want to know if I start over here, I hope that's clear that that's stable. any point in the left half plane. I now map that using z is equal to 1 plus st. Suppose I just use something trivial and say, let's let t be 1. Now if I map every point in the s-plane using s plus 1 to get it into the z-plane, what's going to happen in the z-plane? Do you see that I'm just shifting by 1, and now I'm over here? Am I preserving stability with the forward rule? Or is every possible point in the left half plane of the s-plane going into the unit circle in the z-plane? No. The forward rule is not preserving stability. The backward rule does, and the trapezoid does. This is the problem child. So the forward rule is not preserving stability, but the other two do. And we'll pick up with mapping on Wednesday.